channel, and today I'm going to be talking about exact differential equations. So let's begin. So here's the format for an exact differential equation. M of x comma y dx plus n of x comma y dy must be equal to 0. So how is this different from the integrating factor perspective? Well, the integrating factor perspective is not a type of differential equation. Well, how is this a type of differential equation? Well, this exact differential equation has some traits which it has to follow. When we take the partial derivative with respect to y, we get, let's say, z. And when we take the partial derivative with respect to x over here, we'll get q. And z and q must be equal. So this is a trait of the exact differential equation which it's going to follow. So this is a type of differential equation too. So now let's actually look at the algorithm for solving this. To solve it, we first take the integral of m of x comma y with respect to x. Then we're going to get m of x comma y, and we're going to sub it with 1 just to denote that we have taken the integral. Then instead of adding a plus c, we're going to be adding the phi of y. So now that we have added this phi, which is spelled P-H-I, not F-I-V-E, we're going to now use this other method. So now that we have done this, we're going to take the partial derivative with respect to y of m of x comma y, and then with sub 1, plus phi of y. So now that we have done this, this will just be equal to m of x comma y sub 1 primed plus phi of y primed. And this is going to be equal to n of x. N of x comma y. So now what we're going to do is we're going to solve for phi prime of y. So we can write it like this, phi prime of y. So once we do this, what we can do is, so now that we have done this, we can, right now, just solve for phi prime of y. So we get phi prime of y must be equal to some value, and we can write v for the value. We integrate this, so, and we can write v sub 1. So v sub 1 must be equal to phi of y. So we take this v sub 1 and we input it into this part of the differential equation, and we input the v sub 1 for the phi of y. Then we're going to use this as our answer, and we're going to set it equal to an arbitrary constant c. So this will be our answer. So we can just write m of x comma y sub 1 plus v sub 1, and v is going to be something which we just don't know yet, and then we're going to set this equal to an arbitrary constant c. So this will be how our format of our answer will be like. So now let's actually use this to solve for an example problem which we have written over there. So let's do this. So we can erase this right now and do that. So before we actually start solving, we have to test for exactness. To test for exactness means that what we have to do is we have to see if the partial derivatives are equal. We know that it's set to 0, so we don't have to worry about that part. We just have to look at now if the partial derivatives are the same. So remember, though, if we put a y prime over here, we can take the dx and put it for the m of x y term, and the dy and put it for the n of x y term. So we can rewrite it over here. So bring it over here. 9x cubed plus 2y minus 17x squared, and then we can put the dx over here, plus 7y squared plus 2x minus 5y, and then dy. And we can put a space over here just to say that we're not multiplying it, we're just differentiating with respect to x, so dx. So now what we're going to do, and remember you have to put equal to 0, we have to see if the partial derivatives are the same. So the partial derivative with respect to y of this term, well, this is going to be 9x cubed cancels out. 2y is just going to be 2. Then minus 17x squared also cancels out. Then over here, we're going to take the partial derivative with respect to x. So over here, so 7y squared cancels out. 2x is just 2. And then minus 5y also cancels out. So 2 is equal to 2. So this is an exact differential equation. So now we can actually use the method to actually solve this differential equation. So we can erase this and actually now try to solve this. To solve this, what we do now is, first, what we're going to do is we're going to integrate m of x, y. So we're going to integrate 9x cubed plus 2y minus 17x cubed. 17x squared, actually, because we wrote squared over here, 17x squared. So to do this, what we're going to do now is this will just be, and remember we have to put with respect to x, and then this will be 9x cubed is just going to be 9x raised to the power of 4 over 4, and then plus 2yx, because that's the integral of that, and then minus 17x cubed over 3. And then we're going to add, instead of a plus c, we're going to add phi, phi, of y. So phi of y. And now that we've got this, we're going to take, so we can state that this is equal to each other. Now, what we're going to do is we're going to take the partial derivative with respect to, we took the differentiation with respect to x, so we're going to do y right now. So 9x raised to the power of 4 over 4 will just cancel out. 2yx will just be 2x. Then minus 17x cubed over 3 will also cancel out. And plus phi prime of y, which we can write. Now, we're going to set this equal to n of x, y. So this is equal to 7y squared plus 2x minus 5y. So 7y squared plus 2x minus 5y. Right now, we can subtract the 2x. And we can get that phi prime of y must be equal to 7y squared minus 5y. So we've got this. Now let's actually take the integral. So phi of y must be 7y cubed over 3, then minus 5y squared over 2. Okay. So we've got this right now, and remember that we're going to separate this, so this is not related to that, but we've got this, and now we just input it into our function over here. So we can write this in our answer. So we have 9x raised to the power of 4 over 4 plus 2yx, then minus 17x cubed over 3, then plus phi of y, well, phi of y is just 7y cubed over 3 minus 5y squared over 2. And we're going to set this equal to an arbitrary constant, which is c. And this will be our answer. So let's review the steps which we have just done, because it's actually been a lot of work which we have just done. So let's actually review. So first, we had our problem. And we took the integral of m of xy, but before that we tested for exactness, and we got 2 is equal to 2, which is obvious. Then what we did was we integrated m of x comma y, and we got this value. Then we took the partial derivative with respect to y. Since we took the integral with respect to x, we're taking the partial derivative with respect to y. Once we did this, we get an arbitrary constant phi of y, but we already got it over here. So the phi of y is over here. So when we took it, we get 2x plus phi prime of y as our partial derivative. So we get this after we did the function of this. We get 2x plus the phi prime of y. And we're setting this equal to n of x comma y, which is 7y squared plus 2x minus 5y. Now, we subtracted the 2x to get phi prime of y is going to equal 7y squared minus 5y. Well, now we just bring it up here and we took the integral to get 7y cubed over 3 minus 5y squared over 2. Then we substituted back into this function. And remember, we're not taking the partial derivative anymore because we already took it, got this, and then so the partial derivative right now is gone away. Once we're done taking the partial derivative, we don't have to take the partial derivative again. So this partial derivative we can ignore and just take this value, input for the 5y, and then boom, we get our answer. And remember, we have to make it equal to an arbitrary constant, c. So now that we have just solved this exact differential equation, let's look at some examples to test for exactness, because exactness is really important. Because if we do solve an exact differential equation and it's not exact, then the method could be wrong. So let's actually do some testing and let's erase the work. So now what we're going to do is I'm going to make some random functions over here next to it, and what we're going to do right now is we're going to just see if the test for exactness is true. So let's start. So let's take 4x squared plus 2y and then plus 5xy, and we're going to have plus 9x squared plus 4y minus 2, and then we're going to put y prime is equal to 0. So let's test for exactness. Well, to test for exactness, what we first do is, once we take the partial derivative, so once we take the partial derivative on top, well, we have to take with respect to y, so we'll just get 2, and then the derivative of 5y, well, that will just be 5, so we get 5x, and then we're going to get plus 2. Then over here, we're going to get 9x squared, which the derivative is going to be 18x. And then 4y is going to cancel out, and minus 2 is just going to be also canceling out. So we'll just get 18x. And are these two equal? Well, we can set them to be equal, but essentially they are not equal. So now that we've just discovered that they are not equal, this test for exactness is not equal. So this is not an exact differential equation. So now that we have covered one example, this video would come to an end. If you like this video and if you like this channel, please subscribe to learn more. Thank you.